Okay, any questions before we begin? Any questions on electricity, electric potential, potential energy? Sun. Well, it's more or less neutral. There is no reason for it to be charged. The vacuum, that's neutral. What we call the vacuum is neutral. But of course, you can put some charge there, but it's no longer vacuum in that case. Okay, so in the definition of the potential, okay, in the definition of the potential, if you remember, we define the potential as the work done as you go from A to B. This was equal to the integral of f dot dl from the point A up to the point B. And we said that this was omega B, no, or a function of B minus u of B plus u of A. Now, what can we measure in reality? Well, we can measure the force. Since we can measure the force, we can calculate this work. And so we can determine what this work is, the total work done. If we can determine this total work done, we can determine the potential difference between these two configurations, let's say. That is the only thing we can determine. We can only find the differences in the potential. We cannot determine the value of the potential itself. So this tells me that let's say u of B is equal to minus, from A to B, f dot dl plus u of A. Now, since we cannot determine the value of u at every point, we can only determine the differences, we have to fix the value of the potential at a given point. So let's say if my charges are, one is here, one is there, the other one is there, the other one is there. When this is the configuration of my charges, I say that the potential energy of the system should be 0. Or I can say that the potential energy should be 5 joules. It's up to you, whatever you choose. And then you can measure how much the potential energy of the system changes as you change your charges from the initial state, the reference state, to your final configuration. You only measure the difference. But to determine the potential from the measurement of differences only, you have to define what the potential energy is at a given configuration. That is up to you. That is your choice. The general choice is that you say that if you have a system of charges, if they are infinitely far away, you say that the potential energy of this system is 0. That is the general convention, let's say. In one case, we will see that, okay, from the potential energy, we define the potential. But if you calculate the potential of an infinite wire, for example, in such a case, you cannot say the potential is 0 at infinity. Well, that's a different case. We will come to that in a moment. So that is why we always have this reference point, just fix one point. You have to, it's up to you, whichever point you want to choose. Just choose with some point and define the potential energy of that point or that configuration. Again, that choice is again up to you. Just choose whichever one you like. But once you choose your point, choose the value of your potential energy at that point or that configuration, the potential energy of all other configurations or all other points are fixed. There, you don't have any more freedom. Other questions? Potential created by a dipole. Now, the dipole, we have this one. We have this a positive charge and a negative charge. This is what we call a dipole. And then whenever we want to calculate the potential, let's say, at a given point, then it's just the sum. Let's say this is R plus, this is R minus. The potential at the point P is Q over 4 pi epsilon 0, 1 over R plus minus Q over 4 pi epsilon 0, 1 over R minus. And then we said that this is equal to Q over 4 pi epsilon 0, R minus minus R plus divided by R plus times R minus. Then, of course, we need to obtain some approximation for this. And what we do is we just put the origin at the center of the dipole. Then the distance of the position P from this center, we just call it R. So that tells me that R plus is almost equal to R. And similarly, R minus is almost equal to R. So 1 over R plus times R minus is almost 1 over R squared. This is this term over here. Now, of course, if we say that both of them are almost equal to R, R plus minus R minus is 0, minus R minus, this is not equal to 0. This just tells me that, remember, this is equal to R plus some terms, which will be proportional to, let's say, this is D, R times D over R. And R minus will be minus something R times D over R. Now, R plus and R minus is equal to these R only if we can ignore these terms. So what are the order of magnitudes? In a typical case, you have the R, the size of the dipole is the size of an atom, and R is, let's say, 100 times the size of the atom. So if this is 100, this is 100 times 1 over 100, so this is just 1. So by saying that R plus is equal to R, we are making an error which is 1%. So if your measurement devices are not so precise, then you can just ignore 1% and you can compare your theoretical evaluation with the experimental value, and they will agree within errors. Now, of course, in this difference, if we ignore this one, we should be measuring 0. So that's why in this difference, we keep these terms to evaluate this one. Well, another way of looking at seeing that difference, calculating that difference, is just to look at this isosceles triangle. So this is R plus. This distance over here is R minus minus R plus. So this is just another way of evaluating this difference. Now, if you look at over here, this distance is R plus. This is R plus. So here we have an isosceles triangle. And this isosceles triangle, this angle is very small. Since it's so far away, that angle over here will be very small, very close to 0. If that angle is very close to 0, these angles over here will be very close to 90 degrees. And if you just approximate these angles by 90 degrees, there we have a right triangle here. And furthermore, if this angle is theta, this angle over here is also theta. And we see that R minus minus R plus is nothing but D times sine theta. And so the potential at the point P is Q over 4 pi epsilon 0 D times sine theta over R squared, which we also wrote as the dipole moment times R hat divided by 4 pi epsilon 0 R squared. Now, to calculate this one, we can just say that R plus is equal to R plus plus R minus over 2 plus R plus minus R minus over 2. So if you just sum them up, R minuses, they cancel. We have the R plus. Well, R plus and R minus, one is larger than R, the other one is smaller than R. If you take the average will be even closer to R. Plus, We already evaluated R plus minus R minus. So here we have the R minus minus R plus. R plus is R minus 1 over 2 d sine theta. Approximately. And you see that the coefficient over here, which I didn't write, it just turns out to be minus 1 over 2 sine theta. Just a number close to 1. And for R minus, the only thing you need to change is change the sign over here. Change the sign over here. That is R plus 1 over 2 d times sine theta. Or another way of writing both of these things, R plus minus is equal to R minus plus 1 over 2 d sine theta. R 1 plus minus 1 over 2 sine theta d over R. And quite often we write this as this is R1 plus some number of the order of d over R. So this is just a notation. It just tells me that here that these terms contain d over R squared, d over R cubed, etc. So this is a number which is of the order of d over R. Just notation. This line is notation. Other questions? This one. Well, let's see. This angle over here is pi over 2 minus theta. This is my p vector. And this is the r vector. So p scalar product with the r vector, no, p and the r vector, this angle is pi over 2 minus theta. So if you take the scalar product is just the product of the magnitudes. Well, p has the magnitude p, r hat has the magnitude 1, and cosine of the angle between the two. But that is pi over 2 minus theta. Cosine of pi over 2 minus theta is just sine theta. So if you look at this final expression of the potential, Q times T is the p magnitude of p, times 1, which is the magnitude of r hat, and sine theta, or cosine pi over 2 minus theta, is the angle between the two. Okay, let me ask you a question then. Suppose I have a conductor over here, which has a charge, let's say, plus Q, and the conductor over here with some arbitrary shape, and it has a charge minus Q. And by some means, we have measured the electric field everywhere, and we know the electric field, E of R. Now I have the same charge conductors at same points. The only difference I make is instead of taking plus Q and minus Q, I take plus 2Q and minus 2Q. So let me just put the subscript Q over here, and then this new configuration will generate some new electric field. Let me denote it by 2Q. What is this new electric field? They are conductors. I just double the charges in each one of the conductor. So how does the electric field change? Four times, 2 times, 0 times, or you cannot determine. Also keep in mind that the electric field will depend on how these charges are distributed in my conductor. So let's say that if in this case most of the minus Q charge is over here for some reason, but in this one the charges are over here, again for some reason, then the electric fields will have no relation with each other. So what will be the new electric field? Well, some of you got the answer. It will be just twice, thanks to the superposition principle, by the way. So this system will just behave like this one superposed with this one, two of these ones. So the electric field will be just twice the original electric field. The distribution of the charges will not be modified. It will be the same. If half of it is over here, the other half is over here in this one, it will be the same in this one. So the relative fractions of the charges in different regions of the conductor will not change if you just double the charges or triple the charges, or if you just multiply the charges by the same number everywhere. So the lesson is that whenever you have such a configuration, the electric field at the point R will always be proportional to Q with some coefficient that doesn't depend on Q all the time. Of course, if you just put some additional charge in this one, but not on this one, this proportionality will not hold. So okay, let me say F of R is equal to F of R, where F of R is independent of Q. Now, if you just change this Q to 2Q, then in that case you will have some other function F. Again, it will be proportional to Q, of course, but the function will change. But this function, F of R, when you have the same charge in both of them, just the difference in signs, it doesn't depend on these charges Q. It only depends on how these conductors are positioned and what are their shapes. But it will not depend on the charge. It will not depend on the electric field created, etc. Now, this will be a nice observation in a moment. You see, we had defined the potential difference. This was minus E dot dl. If you want to define the potential difference, let's say that this conductor is at the potential V1. The other one is at the potential V2. The potential difference between V1 and V2, V1 minus V2, is just start from V2, some point on V2, and go to some point on V1. This is our potential difference. This is equal to minus Q times from R2 to R1, F of R dot dl. This function over here, whatever it is, we don't know what it is yet, but that function doesn't depend on the charge, on the charges. It only depends on their relative position and their geometry, but not on the charge. As long as you don't change the geometry, you don't change their relative position, you are not changing this function. And that function is called 1 over C. Let's put the minus sign, minus 1 over C, so that Q is equal to C times delta V. C is called the capacitance. Well, as a student, I always used to confuse whether it was Q is equal to CV or or V is equal to Q times C. And my professor used to tell me, Well, this trick for the Turkish students, Q is equal to Cevat. Okay, this is how we define the capacitance, by the way. This is the definition. So what you do is to determine the capacitance is if you have some configuration of conductors, put some charge on them, by some means evaluate the electric field everywhere. Using the value of the electric field, calculate the potential difference between these two conductors. And once you have that potential difference between those two conductors, that potential difference will be proportional to Q, and the proportionality constant is the inverse capacitance. So what does it have to do with the capacity? I mean, when you talk about the capacity of something, well, if you talk about the capacity of this bottle, it basically measures how much water you can put on this one. So what is the relation here of this capacitance to the capacity? Well, what prevents me to put more charge? So let's say it has a finite surface area, and let's say that its capacity is, I don't know, let's say 1 microfarad. What prevents me to put one more charge? Breakdown. So what's the breakdown?
Basically, when they exceed the limit, charges will be moving through the air for the...
Which limit?
The maximum limit they can carry.
Basically, that's the idea. So although we know that air is an insulator, let's say, it has a very high resistance, which we will study. There is a limit that if you apply an electric field, let's say, we have the air molecules, or just imagine any molecule. And if you put that molecule or atom in an electric field, the electrons will move will feel a force in which direction? Let's say this is the direction of the electric field, and you put some molecule or atom in between. So the molecule or atom has electrons. So what will be the direction of the force the electrons feel? This is the electric field. Electron, the charges, the force they feel is always in the opposite direction of the electric field. The nuclei, which is positively charged, it will feel a force in which direction? In that direction. So you have your system atom. You are forcing some of these to move in one direction, some of them to move in the opposite direction. Well, of course, the nuclei and the electrons, they also attract each other. So if you are not applying a strong electric field, that means nothing will happen. They will just, they will be shifted a bit, but that's it. But if you increase the electric field, then you are applying a larger force, and after a limit, you can just break these bonds. You can just rip off electrons from this molecule. But if the electric field is large enough, that is the potential difference is large enough between 2 points, let's say. In that case, you will be ripping the electrons from the molecules or atoms. But if you rip the electrons from molecules and atoms, you have a system where the charges are free to move around. So that becomes a conductor. So that is what we call the electrical breakdown. So if you apply a sufficiently large electric field, or if you create a sufficiently large potential difference between 2 points, even in air, and then you will see this lightning. Well, that is basically what lightning is. So the electric field created, or the potential difference created by the cloud, is so large that it creates a plasma from air. And the plasma is highly conducting. So basically, if you have a configuration that has a very large capacitance, for a very large value of charge, the potential difference will be very small that you create. So there won't be any electrical breakdown. But if you have a system that has a small capacitance, then even after a small amount of charge, the potential difference might become very large, and that means there will be an electrical breakdown, and all the stored charges, they will just flow through the formed plasma. So that is the relation between this capacitance and the capacity. It is a measure of how much electric charge you can store in a given system, in the atmosphere, let's say, or in a given environment. So the larger the capacitance, the larger the charge you will be able to store there before you reach the electrical breakdown. Now, this is the definition. Then we need to calculate it. What is the capacitance of certain things? Well, the capacitance you can define for any system. The only thing you need to have is you need to have two conductors. They can have arbitrary shape. They can be positioned in arbitrary places. You put some positive charge in one of them and a negative charge on the other one. The same amount of negative charge on the other one. And that makes a conductor. That's enough to make a conductor. And of course, the calculation of the capacitance will be complicated. But nevertheless, that is a conductor. If you measure the potential difference, you can even determine the conductance of the object. Let's look at the parallel plate capacitor. Yes?
What's the case of the lightning?
It is the potential difference between, let's say, the clouds and the atmosphere and the ground.
You say that it's neutral. It's either the same.
Well, you see, in the case of the lightning, is there an electric field created?
Yes.
Does that create a potential difference? Or, I mean, even an electric field is enough. Is there an electric field? Yes. Is it big enough? If it is big enough, then you will have the lightning.
What if it were -4?
Well, you see, here, Q is called the charge of the capacitor. But there is, don't get confused, the total charge of the capacitor is 0. There is no charge in the capacitor. Q is just, you just take the positive plate and the charge of the positive plate. Or you can just say that Q is the absolute value of the charge in one of these conductors. That is what Q is. Delta V always is defined to be, at least in the case of a capacitor, delta V is also always defined to be positive, and C always defined to be positive. To get rid of this minus sign. Now, in this equation, everything is positive. Here, everything is defined to be positive. If it's negative, just take the absolute value. So just to get rid of that minus, so that I could postpone this question, I had this minus sign.
There is a, I don't know what it's called. There is this glass ball thing, which there's but there's this toy at home. It's kind of a toy. I don't know what its name is. Yeah, and inside it there is a rod fish. From it comes all those lightning kind of things from the outside.
That's not a Tesla coil. No, neither. You will be disappointed by what it is. I don't know. but it uses ultrasound waves, as far as I know.
All the electric things are concentrated on my hand. I don't know why.
I mean, the next time, go with a friend, touch it, so that all the electric field will go on you, and then after that, touch the nose of your friend. And get ready to run. Well, as far as I know, it works with ultrasound. I mean, it has some ultrasound in it. Secondly, it's inside is vacuum. It doesn't have the full pressure, so there's little atmosphere. So that's why, in fact, you see all these blue things. Because if you drop the pressure, it's easier to ionize it, so you form what's called a plasma. And those are electric currents. When you touch it, you are basically being charged. And when you touch your friend, he will get and you will also get this small spark, but the nose hurts more than your finger. And then those small lightnings are actually small lightnings. They are the electric sparks. And when you touch it, you are basically creating a current. You are closing the circuit, and so it prefers to go over your body than the glass. I mean, just choose whichever one you like. I mean, if you want to deal with signs, of course, put minus signs wherever you want. But this is basically the definition where everything is positive. And don't worry, we will be dealing with the signs. Well, if you consider both of them, the total charge is always 0.